Okay, so today we will come to the very important philosophical issue about quantum field theory. And this issue is functional integral. What it is and how could we think about its problems. Standard point of view is that functional integral is the axiom of quantum field theory. And the functional integral has a problem. It has a problem of quantum field theory. I would like to show, I am having opposite point of view. For me, functional integral is just a method for me. Functional integral is just a method.
Probably still focusing. All right now.
It's just a method to get QFT. And you know, sometimes it happens that method is not working. So it's not a problem of QFT, it's a problem of the method. And so, Tim, how to translate into English притча?
A parable.
Okay, thank you. So I'll start with a parable. And this parable is, imagine that I am going to solve the following equation. Question is to solve y. In terms of x. And suppose I know only polynomials. Okay, I cannot solve it in polynomials. So y could not be a polynomial. It's clear. Because would it be a polynomial that the highest term in polynomial would not cancel here? So what should I do? Let me try to look at something that is close to polynomials. And these are formal and these are serious. Okay? So let me come back to the time of Newton. Serious. So what should I do? I should say that y is a naught plus x a1 plus x squared a2 plus etc. Okay? And let me try to plug it here. What would I get? A naught x plus a1 x squared plus a2 x cubed plus etc. plus a naught plus a1x plus a2x squared plus etc. equals 1. So let me compare it term by term. First thing is, I know that I know that a0 is 1. Well, second thing, what about a1? A1 is minus a0, so it is minus 1. Now, what about a2? A2 is minus a1, and so on. And this theory never stops. So, an is minus 1 to the power n. So what is y after all? One minus x plus x squared minus x cubed plus x4 minus x to the 5, etc. Good. And then what can I say about y of 1? It is 1 minus 1 plus 1 minus 1 plus 1, etc. So I have no idea what it is. No meaning. And in this parabola, I will call this theory divergent, and let me call it divergent. And if I'd like to understand what is y of 2, it is, of course, 1 minus 2 plus 4 minus 8, etc. Something that is even more crazy, okay? I have, so this is not convergent at all. So suppose I am a mathematician. I would say that this has no meaning. I would say divergence. I would say this thing could not be solved. You see, I'm trying to solve it. I'm getting something crazy. However, I know how to solve it. And y is 1 over x plus 1. So now, let us see what is y, what is 1 over x plus 1. It is a function with domain that definitely containing positive numbers. So of course you understand that maximal domain is this. You just need to exclude -1. But I don't want to go that deep. My equation was to understand y at 1 and then 2. Its domain contains this 1 and 2. So I just need to take the value of x plus 1 at 1 or at 2 and just divide. So it's something understandable. However, method could not be applied. You see? So the fact that method could not be applied does not mean that the problem has no solution. It has meaning. This is 1 over 2. And this has meaning. It's 1 over 3. So here we have the problem in the method. It's actually Taylor method or Newton's method. But problem in the method is not a problem of original problem. So you could be confused only if you think that your method is the definition. That's why we were talking about actual definition of quantum field theory. And we should not switch method and definition. Okay? So here I gave you this parabola. Now let me illustrate this. So Feynman said the following. Great Feynman said the following. If you have classical field theory, and classical field theory means that you have an action that is an integral of the Lagrangian that depends on phi, d phi, etc. And you integrate over sigma. Oh, I called it x. Then we are studying functor. Apply to x, that is a cobordism. We said that in the tropical, we said that for tropical, codomain of the functor, this thing is S critical. S critical. That is S on phi classical that were depending on phi on the boundary. So what great Feynman said? how to go from tropical codomain to tensor algebra. You to find me. He said that functor on x is integral of d phi e to z. Okay, he likes complex unit, complex, he likes this I, s of phi. And here the integral is taken over phi that has prescribed value at the boundary. So this is the Feynman prescription for the construction of a functor. You see, I am already changing the philosophical attitude to the problem. For me, the problem is to construct a functor, and Feynman integral is just a method. Oh, you see, now we have Jesus now. Now I have Jesus number. Very good. For some other people, they say that this is the main thing that we are studying. And it just happens that it is a functor. But I insist on my interpretation. That functor, according to Feynman, is this. So this is a Feynman definition. And you see, it actually takes values. What is a codomain? It's a tensor algebra, of course, on functions of phi gamma. But when you have tensor algebra, you need to specify the ring, okay? And for Feynman, the ring was the ring of polynomials on H. So this is Feynman, so this was Feynman definition. Now, if I evaluate at H equals to 0, I go back to interpretation of classical theory. But Feynman insists that for H not equal to 0, you have this definition. Actually, it was not Feynman who insisted. It was Dyson who made Feynman to write it down. So as you know, Dyson locked Feynman. So Feynman was going around and talking about it. And then Dyson told him, please write it down. However, Feynman refused to write it down. Then Dyson locked Feynman in a room, keeping the key, telling him, I will not let you out until you will write it down. So Feynman actually wrote it down. And that's how we are getting this Feynman integral. So now we will discuss problems that we will have here. And once again, these would be problems of a method, from my point of view, and not the problems of the function. And later in the course, I'll give many examples of these functors that do not involve this method. Okay? So that's why here I contradict to 99% of expositions of what quantum field theory is. To 95%. So if you would like to judge me by comparing what I am saying with the book, you would say that no. In the book, people write down something different. Yes, I differ from the book. And that's why I think it's fair to pay me from BIMSA to tell you something new. Okay? So there are other people who like this functor approach. Among them, Nikolai Reshetikhin. Among them, Graham Siegel. Among them, Greg Moore. But even Greg Moore, in his recent lectures, is calling functor functional integral. But functor is a functor, and functional integral is an integral. I gave you parabola to explain that you can have this function 1 over x plus 1, where the method of getting it fails. And when people say, we need string theory to quantize gravity, what do they mean? They mean that they have problems in the Feynman's method to construct corresponding functor. So what I would tell them? Please use another method. Okay? So now, after all these precautions, we would study free particle. Not because the system of free particle is not known, but because it's a good place to see problems of Feynman's method. Okay? So, action for the free particle is m over 2, integral from 0 to t, x dot squared dt. That's it. Let me try to apply it here. I would say that the functor applied to the interval of the length t capital is integral over fields dx, infinite dimensional integral, with the condition x of 0 is x1, x of t is x2. E. Okay, let me put I here. I would like to do it exactly like Feynman did. So notation, so x dot is dx over dt. So you may ask, what can I say about this measure? I would say the measure is defined as car measure on a torso. So I hope you know what the torso is. So torso is actually a space such that Lie algebra acts on it freely and transitively. So example of the torso. Rn is a torso for Rn. So this is an n-dimensional plane. And this is an abelian group, or S1 is a torso for SO2. And the difference is that in SO2 you have a distinguished element called 1. And here you do not have a distinguished element. So if you have a group, you have a Haar measure on a group. And that's why you have Haar measure on the torso. So this measure is defined up to an overall constant. And of course, we do not know this overall constant yet. So to say that it is Haar measure, it's not enough. It is Haar measure with some constant. That I will call C of t. So what I want to say is that this plus y is this for any y. Tim, is it clear?
Well, not entirely. So, the space, it's well, probably the space of functions. And what is the Lie group? Oh, well, yeah. What is the Lie group? Is it the group of diffeomorphisms?
No. Okay. The Lie group is the following. Suppose you have a function form, and a affine space. You can add to a function another function. So functions form an abelian group. F1 times F2 abelian is F1 plus F2. Okay? Now, here I have functions of this type. Functions x of t such that x of 0 equals x1, x of t equals x2 do not form a group. Okay? However, functions psi of t such that psi of 0 equals psi of t equals 0 do form a group.
You mean in linear space, maybe?
Yes. So they form an infinite dimensional linear space. Psi of t with this condition.
You write group, and I confused for it.
So linear space is an
Yes,
abelian group.
it's abelian group. Okay, yes.
Now, functions x of t such that they satisfy these boundary conditions do not form a group, but they form a torso. If I have one of such function, I can add to it element psi, and I'll get another function of the same type. And you may easily check that the action is transitive and has no fixed points. Okay? Tim, is it clear?
Yes. Mm-hmm.
Okay. So that's what I mean here. So if I shift, the measure would be the same. And now I will use this property of the measure to compute or to start computing this integral. Oh, I forgot important thing. I forgot h bar. So what should I do? I would say that I decompose x of t as x classical that depends on as a parameter on x1, x2 plus psi. And this decomposition is unique. So x classical has explicit form. It is x1 plus t over t x2 minus x1. Okay? Now, action on x classical plus psi is action on s classical plus action on psi. Why? Why don't we have a mixed term? We don't have a mixed term because this is X classical. I can even write it like this. S is a quadratic form. So I'll write it like this. X classical plus S classical psi, coefficient 2, plus S psi. Now, I say that this term equals to 0. Because X classical is a critical point of an action. That's why it has no term linear in psi. Great. Now I can compute. I can compute this term. So believe me that the speed is x2 minus x1 over 2. So this is x2 minus x1 square over 2. And here I have I, and here I have h bar. Okay, so I will put it later. So here I computed this classic. Now I plug it here to get integral over d psi. Once again, psi at 0, psi at t equals to 0. E I over h. Integral from 0 to t. M over 2. Psi dot square dt. Times e to the I over h. x2 minus x1 square. And here I have 2. Okay, I have m here. 2t. So it's a marvelous thing that I got. The marvelous thing is factorization. This thing does not depend on x1, x2. So this term is some number C. That depends on what? It depends on M. It depends on H. It depends on T. That's it. And all X dependence is here. Okay? This dxi was not defined yet. Because this dxi also contains some coefficient, okay, C that may depend on T I don't know about M. I don't know about H. So which is the measure? So Richard Feynman assumes that this measure is H independent. Because when you write it like this, you say H is only here, right? I will put it like this. Feynman is unclear about H dependence of big psi. If you write it like this, it looks that there should be no H bar dependence. You just write it down. But I say we will see. Maybe there is H bar dependence. But of course, we can have something that depends on T. Right? Now, what I would like to say, that when things are written like this, I would say measure xi should not depend on M. Because M is considered to be a piece of the action. How can it be that measure depends on M? Because if measure depends on M, H, and T, what is the meaning of putting this term here? Maybe we may say that this coefficient C, T, M, H bar is regular, and singular piece stands only here. So when you try to open books on functional integral, you will not even see such discussion. People write it like this, and they are saying, take it. Okay? But we are not going to take it like this. We would like to study what's going on. Let me see. Now it's a time for a break. So do we have any questions? Tim?
Well, maybe this one. This dependence, which is, well, unclear whether there is or not any dependence on, say, H bar. We should think about it from the beginning, or should we say that it appears after we split our X into X classical and Xi?
You see, first we need to have the rules of the game. So the question is, what do we mean saying that we have a measure?
But that problem, it appears in the beginning when we write down the very first integral, right?
Yes, of course, it appears already here.
Mm-hmm.
What do we mean by writing this dx? You see, we are doing mathematical physics. And in mathematical physics, we cannot use words like from our physical intuition or from some particular example. You see, after 80 years of study of quantum field theory, we should be able to give definitions. Okay? And I just want to say that people like physicists like Batalin and Vilkovitsky would say that this dx actually depends on h, but depends on h regularly. So it's very important. If this measure depends on h, independent on h, how it depends on h? Okay? When people are writing down something that they call word identity, when people are doing transformations, they should assume something about this measure. So it is the most subtle question here. And now we will have a 10 minutes break. Okay, I am back. Hello. So one professor said that he would be back soon. And we are waiting for 2000 years for him to come back. Almost 2000 years. But I am back in time. So the question is, can we compute it? Or what can we say about this computation? And of course, we would say that psi is what? Psi, so psi is a sum over k, psi k, sine pi kt. All right? So let us plug it in, and we would have the Gaussian integral. So second derivative of psi gives psi back with the minus sign, and we will get something like pi square k square, psi k square. Sorry, I need to put t here. And I also need to put t here. So it's not that bad. And I also need to put m over 2. And here I should integrate over this d psi k. So these are Gaussian integrals. So result is a product over k and I have a common factor that goes to infinity. Together with m. Okay, I will not take care about this pi's. Let me forget about this pi. But I actually have this miht to the power of infinity, and here I have this k to the power minus 1. So it's something strange. This product is divergent. It's a product of all positive numbers, or positive of all integer numbers. So k not equal to 0. So it is crazy. So what are we talking about? Now, we also have here h to some crazy power, infinity. What could it mean? So I will say that naively, we fail. Okay? No meaning. In my parabola, we already had something like this. We had some infinite sum that turned out to be finite. Now, we may play another game. We will return to Feynman in a moment. But let me play another game. I have this crazy integral that I will call CTMH. Could I say something about CTMH from the functoriality property? Get CTMH from functoriality property. So I write CTMH e to the IMH x1 minus x2 squared over 2t. And I want this thing to be functorial. So what does this mean? X1 minus x2 h 2t1 e to the im x2 minus x3 h 2t2 c1 c2. I want this to be equal to c1 plus 2 e to the im x1 minus x3 h 2 t1 plus t2. If I integrate over x2. So it is an interesting statement, interesting condition. I am looking for some C1, 2, or 1 plus 2 that solves such an equation. So what I know that in the tropical limit, h equal to 0, everything works. Now I'm trying to go beyond tropical limit. So C means go beyond tropical limit. And then it could be that such C just do not exist. Because it's kind of a functional equation. So I need to be accurate about coefficients. So what are multipliers when I integrate over x2? So when I integrate over x2, I have IMH2, and here I have x2, 1 over t, okay, sorry, squares. 1 over t1, 2t1, plus 1 over 2t2. All right? So what would be coefficient when I'll take this Gaussian integral? Coefficient would be 1 over square root 1 over 2t1 plus 1 over 2t2. I'm taking a Gaussian integral. And here I have C of T1, C of T2. And I actually want this to be equal C of T1 plus T2. Is it possible? It is a very important computation. And I can actually do it in front of you. C of T1, C of T2. And then I have this difference in denominator. Square root T1 plus T2. T1, T2 equals C of T1 plus T2. Okay, I'll omit this one half. I don't care. So it's a functional equation. Not all functional equations have solutions. But now I can simplify it. I see that C of T1 times square root of T1, C of T2 times square root of T2 equals C of T1 plus T2 square root of T1 plus T2. Huh? So this functional equation has a unique solution. C of T is 1 over square root of T e to the minus epsilon T. So you see, this crazy integral that we thought has no meaning, has a value. It's very funny. You have no meaning, but you have a value. In my parabola, we had exactly this situation. No meaning, but a value. So what does it mean? It means that we are doing something wrong. Okay? And if we are doing something wrong, let us do it right. Okay? So the main problem in all this business is that we were trying to treat determinant as a number, as a function. Actually, it is not a number, it is not a function. It is a D module. Okay? You see, that's why it is good to study some mathematics. Because when you go to physics, you are stuck. You don't know what to do. So who could help you? No one could help you. the only person that could help you is the condensed wisdom of humanity. And wisdom of humanity, okay, I need to write it down. Wisdom of humanity is condensed. Condensed, I think with C. In mathematics. And that's why physicists should know mathematics. Because it's impossible to invent everything by yourself. Most of things were already invented. So let me tell you what the module is. Suppose you have polynomial. Polynomial. And you want to increase the space of functions that you have. Of course, you like polynomial. In my parabola, you increase the space of functions by allowing division by some other polynomial. Okay? But they used to have value. And now we add to polynomials what? Formal solutions to differential equations with, say, rational. Okay. Okay, polynomials, then P over Q, rational functions. And then you add to the space of functions formal solutions to differential equations with the rational coefficients. In particular, you would like to add thing that is called this log. It is neither polynomial nor a rational function. However, you can write down equation. Okay? So you're adding to the space of rational functions these solutions. And then, when you do this, you know what is rational function, R, times this F. How do you know? So what do you know about it? You know how R prime multiplies it. And you also know how to differentiate. You define it to be dr over dx, that is again a rational function, plus r df over dx. But you know what df over dx is. So you can multiply these functions by irrational functions, and you can act on it by differential operators. That's why this function generates what is called D module. D, it means the module of the ring over the ring of rational differential operators. Okay? So now our strategy for this infinite dimensional determinant would be to understand it not as a function, would be to understand it as a solution to some differential equation. So when you have log, you can ask a stupid question. Something like, what is the value of log? And then you will say, the value of log depends on the branch. So it is a stupid question. But you can ask other questions. And other questions would not be that stupid. In particular, here we would like to get this 1 over square root of t. It is not a rational function. However, d over dt applied here is, of course, minus 1/2 1 over t 1 over square root of t. So derivative of this guy could be expressed in terms of this guy and the rational function. And that's why you are not talking about the branch. So, with all this knowledge that comes from the wisdom of humanity condensed in mathematics, we will try to address the question about our poor determinants. Okay? So we want to understand this, right? Let me try to understand another thing. You see, I put here omega squared. Why I call this omega squared? Because if I have x dot square, it's a free particle. But if I put here omega squared times x squared, it's an oscillator. And I want to generalize my problem to the oscillator. And then, looking at the oscillator, I'd like to write down some equations. So actually, I'd like to understand what this is. And this is expected to be some function of what? Function of t and omega. So my strategy would be to write down some differential equations here. So actually, I'm going to study the following product. Product over k squared plus omega squared t squared. So what can I say about it? I can say the following. This object has no meaning. However, what if I do the following? So this is f of t omega. But then what would happen if I divide f of t omega by f of t0? It will be this. Now I have a chance So probably you know this formula. As a function of omega t, it has zeros. And of course it is sine. So let me see the timing. It is a sine.
Shouldn't it be a hyperbolic sign? It doesn't have any zeros on the real line, only on
Yes.
the imaginary.
So you see, it depends. So
Oh
it
yeah,
depends
on the relative sign. Yeah.
You see, so I don't care. So I don't care about. So here is minus k. So in this case it's sine. But you may study you see, you may study both of these problems. And then when you understand that it is sine, and then later on you can take omega and tend it to 0, you will get exactly this linear dependence in t. And we will talk about it later on. So this is one way to understand what is going on. However, now let me tell you the module way. So what I have done, I studied the function and I studied the ratio of values of this function at two different points. So actually, would I consider log of it? It would be log f of t omega minus f of t0.
Minus log.
Minus log. Thank you. Now, how can I study this thing? I would like to study it in the following way. I don't know the value, but I would like to know derivative. I would like to write down differential equation for f. So f is what? Is log of this. So it is a sum of, okay, k squared plus omega t squared. Has no meaning. It has no meaning. I am not afraid. I call this z. So I know that I can consider the, so it is log f. No, it is a. It is log f. I may consider derivative.
That's the sum of logarithms again.
Yes, thank you. I can consider derivative. It would be a sum. And here I'll see k squared plus z squared. And here I have 2z, right? And this is already convergent. But I may fail to understand where does it converge to. Then I'll take the second derivative. And I'll get something. So exercise. Get equations for sine z out of this. I'm not going to do it. You see, as another professor said, I am not a salvation. I give you the way. Okay? I also give you the way. Okay? And then, how do people understand it in terms of so-called Feynman diagrams? This derivative is the following thing. You have insertion like this, and 1 over k squared over z squared is a propagator. And this has a meaning. You have a sum here. It is convergent. So while determinant is not convergent, determinant is divergent, its derivatives are convergent. And moreover, this is a story that you will have in any quantum field theory. You are drawing down some Feynman diagram, it is divergent. However, if you differentiate several times, it becomes convergent. So, instead of a function, you get a system of differential equations. So you have a D module. And then, if you are lucky, you can get the value. If you are not lucky, you are left with this D module. And then, this D module could be of finite order or of infinite order. So what do I mean by D module of finite order? You differentiate once, you differentiate twice, you are back. And such things are called renormalizable. But it may happen that you differentiate and differentiate, and still you are getting new objects that are still ill-defined. And in this case, you may call such a theory non-renormalizable. However, even if it is not renormalizable, it is a problem of Feynman approach. Okay? It is not the problem of the theory. So we discussed problems of Feynman approach. Even in one-dimensional case, this poor guy, without insertion, is divergent, while this is already not divergent. For the case of two-dimensional theory, this guy would be something like p squared plus m squared. And instead of sum over k, you will have this integral d2p is divergent in d equals 2. So what to do if it is divergent? You differentiate again. So you don't know what this is. Take the derivative with respect to the mass squared, and you will get d2p p squared plus m squared squared. This is already convergent. So these are tricks with Feynman approach. But this Feynman approach with its tricks is called standard approach to quantum field theory. And my goal was to show that this so-called standard approach is just a method to get functorial QFT. And we already constructed functorial QFT. For free particle we constructed factorial QFT. So this is a function for h not equal to 0. So one can do like this. One can start with a so-called classical problem, okay, and then try to guess this prefactor from the condition that it is a function. And it is another method, not Feynman method, but still it is a method to solve functoriality condition. That is the main problem in quantum field theory. So now we are having a break, okay? Because of Chinese holiday. And after the break, I will describe these type of prefactors and these type of tricks in Feynman approach. Okay? In different dimensions. So I will describe it tomorrow, but tomorrow it is an autumn holiday in China. So the first class after the break would be devoted to these determinants in different dimensions. Okay, mostly in dimension 2, mostly in dimensions 1 and 2. Okay, and now I still have like 5 minutes for questions. So do we have a question?
Well, in the beginning, we assumed that the determinant might depend not only on t but also on m and h, and it is not clear whether functoriality can say anything about those dependents. Like m and h, probably we can say nothing about it, right?
Okay. So we will discuss it after the break. Okay, we will discuss it and the meaning of it after the break. I mean after the autumn break. Because as you see, this T is dimensionful. It could not be like this. So you know how this thing should be corrected. Here, sorry, I always forget M. Here we have T, M, and H all together. And in the factorial formula, we should also have such combination. So I postpone study of this to my class after the break. because I wanted to throw in today a lot of ideas, okay? And after the break, we will have time to discuss them one after another. And by the way, the title of my course was Quantum Field Theory with and without Planck constant. So I am strictly following the line of the title. I never said functional integral. It is just a method. You see, if we come to this professor 2000 years ago, he was talking about salvation. He was not talking about traditional customs. Okay? He was talking about the final goal. So for me, functional integral is like an Old Testament, okay? And functorial point of view is the New Testament. Okay? And I came not to violate, but to improve. So I am not violating functional integral. I am improving it. I am putting it in the full picture at its proper place. Okay? And I want you to think about it during the autumn break. Because what I'm telling you is kind of a revolution in the way how people used to think about quantum field theory. So if you look at say, Edward Witten's lectures at Princeton School, Mathematical Physics for Mathematicians, you would not see anything like this. And in this course, later on, after putting forward the proper set of ideas, we will go to many examples where you could see how these ideas are working out. Okay? So, my time is running out. So, have a nice autumn break. See you after the 6th or 9th. So, let me tell you where where we will meet. We will meet on 9th, on Tuesday. Sorry?
No, the 9th is Monday.
Yes, so we will meet on 10th. We will meet on 10th. And the last, on October, we will have 2 classes on mathematical physics and 2 classes on mathematics by Maxim Levinson. So last questions. Maybe not last questions, any questions.
Professor.
Yes.
Okay, I have a question. Do you mean by the normal integral, it is natural to get some divergent terms? So as I see, we just care the proportion of these infinite integrals, these divergent integrals. So do you mean that in the D module we can explain, in the D module theory, we can explain the algebraic property of this kind of proportion?
Of course.
It is more natural, right?
Yes. So it is more natural, because from D module point of view, you are not studying the value of the period or of something. You study equations on the functional dependency.
Yes, yes. I see. And in the first half of today's discussion, you mentioned the Haar matrix, a Haar matrix.
Yes.
Yes, dx, the Haar matrix. Is it does it coincide with the geometric property, the geometric you say enrichment of the functorial approach to the to these functors?
Let me tell you that everywhere where you see this T, it is geometrical enrichment. So you see it here, you see it here.
Yes.
And the main problem of mathematicians who are trying to understand quantum field theory is that they forget about this geometrical enrichment.
Yes, but my question is the Haar measure also a geometric enrichment in your explanation of the functorial approach to quantum field theory?
So this measure, whatever it could be, is on the interval of the length T. And then you may study the question, how should proper measure depend on T?
Okay, so only T is the geometric enrichment,
Yes,
the parameter. Okay, I see.
Exactly. So the space of functions on the interval is equipped with the metric given by this length.
Yes. But the matrix dx may differ from it depend on the parameter t, right?
Yes, and it is.
Okay.
Because suppose you have two functions, f1 and f2 on the interval. How can you form a metric on the space of functions? You say you take delta f, say 1 squared, but it is a function. And then you integrate over an interval. But to integrate over an interval, you need to put here a measure on the interval.
Okay.
And here you have this geometrical enrichment.
Yes.
But it is how geometrical enrichment come in the Feynman approach.
Okay, so you mean we can forget the integral? We just need the geometric enrichment in your functorial explanation.
So what we need to construct a functor. Feynman integral and everything around it. It is an attempt to construct a function. Sometimes it works, sometimes it doesn't work. Okay?
Yes, yes.
Sometimes we need to use, say, D-module approach to get the result. However, I want to say that this answer is finite. No infinity here. So infinities appeared when we were trying Feynman approach,
Yes.
but they drop out. And this is the outcome. And the full story would be to understand how this finite thing, 1 over square root of t, came out of the infinite dimensional integral. Like in my parabola.
Yes, yes. Yes, I can get it.
Over 2 is 1 minus 1 plus 1 minus 1, etc. 1 over 3 is 1 minus 4 plus 8 minus 16, etc. You may think that here we have strong problems, but this is a perfect answer.
Yes, maybe I guess it may not only be a parabola. Maybe if we integral by terms, by split the function to progressions, this kind of infinite sum will appear.
We already have infinite sums.
Yes.
Because when we do things naively, we have sum over k logarithm k. What the hell is this? Wow, what the hell is this?
Yeah.
So this is as crazy as this. However, the answer would be pretty finite. And now, here the mathematics was mathematics of formal series. And mathematics here was mathematics called localization. Or it's go to fractions. So if you use improper mathematics, you get a lot of problems. If you use proper mathematics, you get answer without this problem. So here you create problems with formal series, and then you somehow try to deal with it. Like you have formal series. This one. So you understand that it is 1 minus z plus z square minus z cube, etc. So you have a region of convergence. And then you study analytical continuation.
Yes.
But this is a problem in Syria approach. But you can just divide 1 plus z for z positive. So if you just divide, you do not need to have all these complications.
Yes, I get it. So we can call Feynman integral as some kind of like formal integral, just in form, we integrate.
So Feynman integral is just an approach to get something. And this approach could have problems inside the approach. And we can modify approach.
Okay.
And sometimes the approach with modification works. But we can use another approach. And in this other approach, we get the result without any problem. So in functional integral, we are creating problems, and then we are solving problems inside the approach. So it is the drawback of the approach, that it creates problems. To be solved.
Okay, thank you very much.
Okay. I don't want to hold you too much. I want to be sharp. 2 hours means 2 hours. Yes. But at the same time, if you are interested, you can write to me, and we can have extra discussions. I'm willing to share my knowledge. Okay. So you are very welcome to join this class due to generosity of BIMSA, who arranged this class and who is paying me for giving this class. Okay. That's why I am grateful to BIMSA and to Professor Yao, who found his personal money to pay me to give this class. Okay? And we will try to make notes to help you to understand the subject. So, and there is U, who is in charge for distributing notes and videos. You may call him, he is Chinese. He would distribute material. U, is it true that you are Chinese? Okay, and you would help other Chinese people to get material, right? Okay. So once again, I have an email that is AS2 at Yandex.ru. You may write to me. We may discuss things that you are interested in. Okay? So thank you for attending.